Hello team, welcome to another video guide, this one for programming assignment 5c, the interpreter checkpoint. We're going to try to print out hello world or something similar. In this video I'm going to skip all of the deserialization code. We're not actually going to read in the annotated abstract syntax tree. You know how to do that at this point in the class and don't want to watch me typing in those sort of lockstep functions for 45 minutes. Instead, we're going to get started with some cool expressions: new, dispatch, variable, assignment, integer, and plus. We're going to try to interpret those correctly. Doing so will require us to think about the environment, the store, and cool values, all from our operational semantics. And along the way, we're also going to talk about the class map, which we will need for new expressions, and the implementation map, which we will need for dispatch expressions. I'll do lightweight versions of all of them. Along the way, I'm going to try to spend some time on debugging and tracing to instill some good debugging habits, because writing an interpreter correctly is very difficult, and ad hoc printf debugging typically does not cut it. We're going to need something more systematic. This is all going to end up with recursive evaluation. We're going to try to run some simple cool programs with copious debugging and see what happens. All right, so our basic plan. We've got an empty directory, and let's call this eval.ml. I start all of my OCaml programs the same way. PA5c, W6y. And we said we wanted new, dispatch, variable, assignment, integer, and plus. So I'm going to have a very simple notion of cool expressions. We can have new, like you can say new main, or I don't know, new point, I guess. You can have dispatch, where you have the receiver object, the function name, and then the arguments. So this would be something like self.foo of arg1, arg2, all the way up to argn. You can have a variable reference, which will just be x. I have it as a string. Note, I am not going to be considering line number locations, but you definitely have to. All right, just to save time for now. So this could be a reference to a variable like x. You can have an assignment statement. This would be something like x gets 2 plus 2. You can have just a raw integer. And in OCaml, I'm going to explicitly note that these are 32-bit integers because that's required for cool. That's a standard gotcha. So this could be something like 1, 2, 3. And you can also have plus expressions, like x plus 5. And again, I am not going to show, right? You would read in the annotated AST to get these. I'm not going to show that. I'm going to assume that we know how to do that by this point in the course. Nope, nope, not that. Go away. Can't. All right. We also want to talk about the environment, the store, and values. And let's talk about cool values first. In the cool reference manual, which we'll just pull up here, before the operational rules, we talk about the syntax for cool objects. Right? So we describe base objects using things like int, bool, or string. So we're just going to have a cool int and a cool bool and a cool string. And another possibility is that we could have one of these more complex cool objects. Right? So we could have a cool object where it has a name, and then after that it has a list, sort of a mapping from attribute names to what I will call cool addresses. And for us though, cool address will just be an int. So I've made it an abstract type so that it looks a little spiffier, but that's really all that's going on. And indeed, there's one other possible value, void, but we're not going to spend a whole lot of time on that. the goal of our interpreter is to boil down expressions into values and to update the store. So at the end of the day, we're going to want some sort of function that takes in cool expressions and some context and produces cool values. Like if we ask it to evaluate 2 plus 2, we want to get out 4. The first one is an expression, the second one is a final value. In order to do that, we're going to need to keep track of the store and the environment. And these are both mappings, right? So recall the environment maps variable names, oh my gosh, to their cool addresses. And we could use a number of different data types. Could use a hash table. We could use some sort of map. I'm going to be super cheap and just use an association list. We will use an association list. That is, if X lives at address 33 and Y lives at address 7, we would just have the list X lives at 33 and Y lives at 7. I'm just going to put the pairs right there in the variable. So for us, an environment is going to be some sort of list, a list mapping variable names to cool addresses. That's a pair. Similarly, recall that the store maps cool addresses to cool values. And once again, we're just going to use an association list. So for us, the store maps a cool address to a cool value. So we've laid out the environment, the store, and various values. We're also going to need the class map and the implementation map. And for us, the class map maps class names to attribute names and attribute initializers. Fix me, I am not doing types. In reality, you would read in the class map by deserializing the annotated abstract syntax tree, which has the class map at the top. Again, for us, I'm just going to skip a lot of those details to save time. So our class map type has class names, and then we've got these attribute name and attribute initializers. So that's an attribute name, and an attribute initializer would be a cool expression list. Similarly, the implementation map maps class name and method name to the method formal parameter names and the method body, at least for us. So, you know, fix me. Check what the full version should really be. So our implementation map, right, it's going to map from, this is the class name, method name, right? If you give me one of those, then I'm going to give you back the formals and the method body. And the formals are a string list, and the method body is an expression. And if you have an association list of all of those things, then that's our implementation map. All right. Let's see how many syntax errors we've made so far. Note, our program does not actually do anything. It's all just type declarations, but that's not going to stop OCaml from yelling at us. Oh my gosh. All right, but look, our program doesn't do anything. Why doesn't it do anything? Because main is still empty. But we have set out our data types in advance, and that's Really important. Now, once we start having expressions or values or environments or stores, we're going to want to print them out. So I'm going to have some debugging, maybe some debugging and tracing support, right? Oh my gosh, do I really have to do this? I guess I do. All right. So we want to have some debugging and tracing support. And I'm going to bring in an interesting little trick from OCaml. All right. Let's say sometimes you're going to want to run your interpreter with a lot of debugging, and sometimes you won't, because remember that your interpreter ultimately prints stuff out, like through outString or outInt, and you may want to see that unimpeded, but other times you'll want to see a lot of tracing. So let's get started doing some conditional printing in OCaml. You can do this in other languages too. So I can have a debug function, and I'll show this in just a bit, but if this debug flag is true, I'm going to be using Printf a lot. I can just smell it. Let's open Printf. There we go. I want to print out this result string in. So it turns out that there's a function in OCaml, and I'm not going to spend a whole lot of time on this, that takes a format string and all of its arguments, processes them into one big final string, but then lets you decide what to do with it. Right, this is called continuation printf, which is spelled with a K because we're bad at naming. So let's see how this works. Debug hello world, because there is the slight possibility that I've gotten the arguments in the wrong order. Let's yay. All right. So there we see hello world, but if instead I were to change this to false, then we don't see anything. Right? And you could have some argument processing that set this. We could have a hyphen debug flag, that sort of thing. So now we have a way of doing conditional debugging, but it's also nice to have a way of taking all of our data types and turning them into strings. And in some languages like Python, you might get this for free. But here in OCaml, we have to do a little bit of work. Sorry. If they say new s, then we will just print this out as new s. If they say dispatch of the receiver object to the function name and the arguments, conceptually, we just want to say dispatch of the receiver object to the function name and the arguments. So do the receiver object, the function name, but we're going to need some way of gathering up this list of arguments into a big string, and we will use fold left, our favorite recursive function. And we'll just take our accumulator and put in a little comma, and then do an expression to string of the element. We will start with the empty string, and we'll do this over all of the arguments. All right. Now, this is going to have one extra comma at the end, but this is just for internal debugging, so I don't care. If there is a reference to a variable, let's call it a variable x, then just have variable x. If we are assigning that x gets e, then we will assign that x gets e. If it is an integer, this LD for long decimal is for full 32-bit integers in OCaml. And if we have plus of E1, E2, then we have expression to string E1. There we go. Much better. So hypothetically, we could have some expression like plus of integer 5. The L just means 32-bit integer, and integer 3. And we could then debug my expression is this, just to make sure that everything's working correctly. My expression is plus of 5 and 3. All right. So we have a way of converting expressions to strings, which will definitely be handy. We also want a way of converting cool values to strings. Okay. If it's a cool int, then we'll just print that out. If it's a cool bool, %b is Boolean, not in C, but yes in OCaml for convenience. If it's a cool string, the manual also includes the length, but I'm too lazy to be bothered. If it is void, you just write out void. And then the most exciting one, when it is an arbitrary cool object, where we have the class name and then the attributes, the fields. So once again, we're going to want to gather up all of these attributes. Right? So this will be our attribute string. We'll go over all of the attributes. But when we have one of these, it's going to be an attribute name and the attribute address that we get instead. So we'll print out the attribute name and say that it lives at the attribute address. Let's just make this a little clearer while we're here. We can have everything you had before plus this variable lives at this location. This is everything we had before. This is this variable. GDR. There we go. And we'll go over all of the attributes. And then we print this out like this, your class name. And then we print all of these things inside it. I'm just using these braces as a notation for myself. All right, so that's a value to string. Line 89. And of course, we don't want to print out the actual attributes. We want to print out this attribute string that we just spent all this time making. Great. All right, so we can print out expressions, we can print out values because our addresses are just in, so I'm just sort of hacking it. We will potentially also want to print out environments and stores. So we have some environment to string function, and you just use the same sort of approach that we had here. Right? Sometimes these things are called bindings. Right? Our environment env, we'll just give it a full name, has a bunch of bindings that go from names to addresses. Hey, we've pretty much already done this. This is great. So we will just return the final result. And we'll have something fairly similar for having a store to a string. This time, though, we will have addresses and cool values, and we will want to print out the address, but we'll call value to string to get a string here. Value to stir. Did I mean? Yes. Curse you, impossible to see font. All right, that's working pretty well. So we can print out expressions, values, environments, stores, and the class map and the int map never change once we read them in. So I'm not going to bother printing those out in any great detail. All right. So now, after all of that work, we can have our actual evaluation, just another name for interpretation. And we want, at the end of the day, an eval procedure that takes SO, SE, and then the expression, and returns to us some new value and a new store. And I'm going to formalize that a bit in OCaml. Our self object is a cool value. This is the self object. S is a store. This is This is the store, which is memory. E is our environment. Did we call these cool store and cool environment? No, we just called them store and environment. Great. This maps variables to addresses. This maps addresses to values. Just a brief reminder. And then exp, which is a cool expression. This is the expression to evaluate. And the return value for this, when we return two things, we return them as a tuple. We return a new cool value and a new store. So this is the result value, and this is the updated store. Where did I get all of these things? Actually, we can read them right off of the operational rules. This is SOSE. I called this expression, and then this V and S prime, those are the return value and the return store. Right? So we're implementing this turnstile. That's our function, and we're basically just going to go read off all of these rules and implement them. Right? So this is our recursive procedure, and basically we would check and see what the expression is. And if it's, you know, an integer, let's go see up here. We've got a bunch of choices. If it's a cool integer I, conceptually we want to return the cool object, you know, int I. That one's going to be easy. All of the rest are going to be super hard. But even for something as simple as integer and plus, there might be some complications. So officially, we're going to return the new value and the new store when we do this. All right. And then once we do that, we'll just return the new value and the new store. Unhandled so far. Haven't gotten there yet. So if we do see this integer I, we need to return a new cool value. So we'll need to return a cool int, and just reading in integers doesn't change the store, so the store remains unchanged. Where did I see that? Let's go see if we can find, here it is, the rule for int. If they say I, then we just make a cool int and we return the same S store that was passed in for us. I'm not using a capital S because capital letters mean something special in OCaml, so we can't do that. All right. And indeed, while we're here, let's see what happens with plus of E1 and E2. And we're just going to, this trick never works. Can we? That doesn't look like quite enough room, but maybe. All right, we'll change the wrapping. We're going to look for the plus rule, which I believe is down here called arithmetic. So we'll actually just take one of these lines and see if it copy paste. It's totally not going to. Yeah, it's not happening. But we can just see it there on the screen. Every time you see one of these turnstiles, you want to just convert it into a recursive call. So we're going to want, this value1 and store2 to be the result of calling eval recursively. SO stays the same. The store is the one we passed in. The environment is the same, but we ask it to evaluate E1. And then after that, we're sequencing them. Now we take this store2 and we feed it in when we're evaluating E2. And that gives us value 2 and store 3. And now our result value, we're going to match V1 and V2. And if we're super lucky, they're both cool integers. Well, actually, we don't have to be super lucky. The type checker ensures that that's going to happen. And if it doesn't, it's probably a bug in your interpreter. So in this case, we can just make a new cool int where we use 32-bit addition, even on a 64-bit machine, to add I1 and I2. And if this is any other combination, We'll just yell and make a note to ourselves so that you can fix that bug later. Once I'm done, I return that return value. And which store do I return? Oh, I return store 3. Because I don't want to lose any side effects, even though we don't quite have any yet. All right. Let's see if this even compiles. All right, compiles so far, which means that hypothetically, we could even get ready to run this expression. Like maybe we can see if 5 plus 3 is actually equal to 8 20 minutes later. In order to call eval, we need a self object, a store, and an environment. And I'm totally going to cheat, right? Our self object is going to be void, right? That's not a good one, but whatever. Our initial store is going to be nothing, and our initial environment is going to be nothing. But then I can have a final value, final store, which I get from calling eval on SOS environment and my expression. And value to stir, I can try to print out this final value. 143, begin and end may be unmatched, which almost always means the problem is above higher, but maybe it's down here. Begin, end, let equals, after this debug I need a semicolon. There we go, let's try again. Ho ho ho! We took the expression 5 plus 3, a cool program, and we produced a cool integer as a result. But debugging everything like this, like only seeing the final value, is not going to be enough for us. We are really going to need tracing. We want to see everything that's happening. So we're going to suggest you can do it. You can be bigger. There we go. Back up in our debugging code, when you're going to evaluate, 5 plus 3, you sort of call yourself recursively and you do the 5, and then you call yourself recursively and do the 3, and then that results in 8. And we're actually going to tab over our printing like that in order to keep track of what's going on. Right? So we'll call this have an indent count, and when we want to do some debugging of this indenting, then string make, then we will make a string that's of this size. And what's going to happen is, as we call ourselves recursively, we will add to this indentation count. Right? So we want a lot of debugging. I strongly recommend it for you. You want debugging coming out the wazoo here. Right? So whenever we enter, I'm just going to increment the indent count by 2, and then right before we leave, I will remove it by 2, or decrement it by 2. And once we're in here, I will tab us over if necessary, and then debug that we are calling eval on this particular expression. Now, potentially, we also want to keep track of the store and the environment when we come in. Store to string, did you mean store to stir? Almost certainly. I meant store to stir. Where were we? I'm going to print all of those out. Unbound value, environment to store, env to stir. All right, all right. Here's the trick with being lazy, is that I can never remember just how lazy I decided to be 5 lines ago. All right, so we can print out the expression, the store, and the environment. Indeed, we could even print out the self object. That we're evaluating. And then, when we're getting ready to leave, I'm going to print out the return value. right, which is called new value. Could also print the outgoing store, but I'm going to be a little lazy. All right. So now let's see what happens when we run this. At the start, the expression is 5 plus 3, and then eval is called on plus of 5 and 3 with no self-object, no store, and no environment. But then we call ourselves recursively to evaluate just 5, which returns 5, and then we call ourselves recursively to evaluate 3, which returns 3, and that whole thing is 8, which we pass up to our caller, which is 8. So sort of standard tabbed over debugging. This isn't very exciting now, but soon we're going to have side effects that will change the store. And that's going to, this sort of debugging is going to be critical to understanding what's going on. To see how that might come up, let's take a look at some of the other expression types that we might want to deal with. And one of these is new. And in order to deal with new, we're going to need the class map in order to know what's available. So somewhere up here, yeah, we had a class map type and an implementation map type. Right? And again, you would actually read these in from the annotated abstract syntax tree. But I'm just going to have one particular class map for now. Right? I'm going to say that the class main, right, has one attribute x, and that x starts out life by being initialized to the integer 5. Right? So this is as if, right? As if, this is as if we had class main x, which is an integer, gets 5. I'm just not actually reading it in because that's not instructive. Okay. So, and we might even, we could have y, which is 3. We would just 3. It's going to yell at me because those aren't 32-bit integers. All right, let's see if that compiles. That compiles. So now that we have one single class map, we can start to evaluate what happens when someone says new class name. Now, this is going to be super complicated. We're going to go all the way and see if we can find new. I am not going to do self-type. You can read more about this later. But one of the first things we do is read in from the class map. Right. We want to get all of these attributes. So the attributes and initializers are OCaml list.mli. How do we get something out of an association list? Association AL returns, so we're looking for whatever they said was the C name, and the list was our class map. Fix me. What if it's not in there? That probably means there was some sort of type checking error, but it could also mean an error in your interpreter at this stage. So we have all of the attributes and the initializers. That's this part there. We've just found out A1 and E1. Right. Now we need to make new locations for all of them. All right, so somewhere back up here where we had our store. We're going to have a really cheap new lock function. Starting at around, address 0, every time you ask for a new location, we're going to give you, address 1, address 2. We're just going to count our way up. Right? Actually, for easy debugging, just to separate out, the numbers that I'm writing from these addresses, let's have our locations start at around 1,000 instead, just so we can tell locations from numbers. All right, so we've got these attribute names and their initializers. And for each one, we want a new attribute location. So I called new location for each one and gathered the results up in a list. What's the next thing that I'm supposed to do? We've made each one distinct. We want to create a new value. Right? We can't copy and paste. That's going to be this new receiver object. And our cool objects have, we want attribute name times locations as pairs. So what I'm going to do is get just the attribute names. By throwing away the initializers for now. And then it turns out that I can get this attribute names and locations, pairs and locks, by combining, this is like a zipping up function, right? The attribute names and the new attr locations. And now I'm in a good position to make this object v1. Right? So v1 is going to be a cool object. Its name is cname. And I misspelled this. Here are its attributes and locations. Right? Now, currently, those are all, we've said they live at locations 3, 4, 5, and 6, but I didn't actually put anything there in memory. So one of the first things we do is we update the store, right? So that in each of those places we hold the default value. I am not, fix me, default values, right? I'm not actually going to do that. I'm just going to give everything like the integer 0. You can look up how to do default values in the manual for later on. So the store updates, right? We take each one of these new locations and we have new location mapped to cool int of 0L, and this is from our new attribute location. So this should be default value, right? But I'm not doing that. Right. So that's our store update, and then S2, it's like the S1 that we came in with. So S2 is like S1, but with these store updates associated with it. And now we evaluate all of the initializers as assignment statements. All right. So come back to me later. This means that we do need assignment statements where I've got some sort of variable name and some right-hand side expression. And we let value1 in store 2. We evaluate the right-hand side and we get out a new store. I'm just going to go back and look up. Here it is, an assignment statement. This was this part. Right? We just evaluated the right-hand side. But now I need to look up in the environment map where it lives. So location L1. We look up variable name in the environment. Right? This is like E of vname. And now store 3 is just like store 2, but with that new mapping. So what we're going to do is first remove any old association in the store. Which store? Store 2, associated with this old address. And then we are going to add a new association right on the front that says that this address holds value 1. So we're overwriting memory, right? Let's get rid of that. Anything you used to have bound to L1 in this store is now gone, and we've updated it with something else exciting. And now we just want to return v1 and store 3. We'll see if we've made any mistakes there. Now that we have handling for assignments, we're now in a position to go back to new and evaluate all of the attribute initializers. And we notice that we've changed the self object. It used to be SO, but now it's V1, which is as expected because these are the attributes of V1. Because we have a list of these attribute initializers, I'm going to fold left over them. We're really only doing this for the side effects. So we're going to have an accumulated store, and then the attribute name and the attribute initializer, where we start with S2, and we go over all of the attributes and initializers. And what we do, we just call ourselves recursively. We have a value that we ignore and an updated store that we get by calling eval. We normally say SOSE, but remember, we got to change that. Here, we're very tricky. We do V1, all right, V1, and then the accumulated store we have so far. And here we have a very special environment where we only have these attributes and locations in scope. Attrs and locations. This becomes our new environment. And we make up an assignment statement from the attribute name to the attribute initializer. And if all of this works, we accumulate the updated store. At the end of the day, you're another day older, we return V1 and this final store. We return V1 and the final store. Oh my gosh, so complicated. Let's see how many type errors we made. Our initial store is just called S. Yeah. All right. So now, what if my expression, instead of being plus 5 and 3, it's actually just new main? That will be interesting enough to try out. And what we potentially want at the end of the day, and let's just double check and make sure we're not forgetting anything. Store 2 is store 1 with all of these default values, right? We want to return all of this. Seems pretty good. Is that we would want to return a value that has its X and Y fields pointing to things that hold 5 and 3 respectively. All right, let's see how that, we have to actually recompile it. All right. Am I running the right? Yeah, okay. This is my old expression. This is my expression. Let's actually run the one I want to be running. Oh, super complicated. So, I mean, this looks reasonable. We're producing a main object at the end, but without being able to see the store, I don't know if we are right or not. Hint, we're probably not right. More on that story in just a bit. So now we also want to print out not just our return, but also, where was it? Could also print out the outgoing store. Yeah, let's do that. Call this like the ret store. New store. So here at the end of the day, we're returning main, where its X attribute lives in 1001, which is 5, and its Y attribute lives in 1002, which is 3. Notice that these didn't print out in the same order, or in expected order, because it's like a mapping, or like printing out a hash table, right? It's sort of random. But I could just add a little sorting before we print out the environment. And now we'll see address 1001. This extra comma was because I was cheap about those string join functions. Our final result is a cool main object where its x field is at address 1001, which is a 5, and its y field, which is 1002, which is a 3. Is that what we wanted? X is 5 and y is 3. It is! That's exactly what we wanted. Well, let's go run it one more time and see how that's happening. Up here at the top, we start with new main. We're evaluating new main. Nothing exciting is happening. But in order to evaluate new, after making all of these new storage and environment locations, we make up the fake assignment statements. X gets 5 and y gets 3. Indeed, let us, just for ease of calling, there we go. Oh, no, we didn't. All right. So now it may be a little easier to see that first we make up x is 5, and then we made up y is 3. But notice by the time we're calling x is 5, we've already made a new environment that says x is 1001 and y is 1002. But initially, the store for both of them holds my default value of 0. To evaluate x as the integer 5, we first evaluate 5, which boils down to 5. That's not very exciting. The return value for that is 5. But now, after the assignment statement, we've changed the store. This is the essence of imperative programming. Notice that at this point, the x location is correct, but the y location is still 0. But then we go into assign into the y location. And you need to do this correctly because it is possible in cool, you could write something like y starts at x plus 3. And this would be 5 and 8. And the code that we have may well handle that correctly. All right, so we have now handled new, which is pretty good. What else is on our list? Well, we did assignment statements. Let's actually just do variable lookup, right? Because that's fairly direct. If they say a variable x, assignment variable, we do this two-stage lookup. First, we find its address L in the environment. Let's just call this our variable name. And then the final value, we look up the address in the store, and we return the final value and the store unchanged. All right. But this does mean, oh my gosh, Steam, do you get to go away? You don't get to go away. Go away. All right. But this does mean that we can go through the example I suggested earlier. Suppose instead y was something like x plus 2. Right? Well, if I want that to be the case, I have to change this to, leave this integer 2, plus of a variable x and integer 2. Plus expects 2 arguments is here applied to. When you hard code these in OCaml, you need a billion extra parentheses. They are quite correct in order to make this work out. All right, there we go. So this should result in 5 and 7. Let's see if it works. All right. Here we've got at the end x living in 1001, and 1001 is 5. And here we've got y living in 1002, and 1002 is 7. And you could trace through, right? Here's the x plus 2. When we're just evaluating x, we know that x lives in 1001, and 1001 is 5, so we return 5. And then over here we have 2, and 5 plus 2 is 7. All right. So we have done new variable assign plus an integer, but we have not done the evil dispatch. So for dispatch, we've got the receiver object, the function name, and the actual arguments. Whew, dispatch is tough. We'll go look through. Here's the dispatch rule. It looks long, but it's not that bad. It says we go through here and we evaluate all of the arguments in turn, and then we do the receiver object. All right, that's a little weird, but we have to do them in exactly the order required. So we've got to do the arguments first. And as we're doing that, we want to note all of their values, but also build up this final store n+1. And there are a number of ways to do this. We could do this with some sort of for loop. Right? We could do it with fold left. We've been very nice and used a bunch of fold lefts up until this point. Let's just show how you could throw in some imperative coding, even in OCaml. We're going to keep updating this big store. And for all of our arguments, right, arg values, we're going to call ourselves recursively, and the arg value and the new store will be the result of calling eval on so, let's call this instead the current store, and call this the argument expression. This is the argument expression. We set the current store to be this new store, and we return the argument value. So now our current store corresponds to, so then in the CRM, cool reference manual. All right, so what are we supposed to be doing now? Now we evaluate E0, the receiver object, right, which I guess I could call E0 just to match up with what they suggest. So now value not, what did we actually call this? Value not, sure. So value not and store n+1, we call eval current store E and E0. So we've evaluated all the arguments. We've evaluated the receiver object, and we really, really hope that the receiver object is actually an object and not like void. More on that story later. Now we need to look up things in the implementation map. We're going to find all of the arguments and all of the results. So I'm going to need to have a hard-coded implementation map. So we said, here's our hard-coded class map, but what if we also had main, which was an object, which just said something like, I don't know, x plus y. Well, if that's the case, our implementation map says that in main's main method, first we give all the formals, and then we give the body. So for us, there are no formals in our particular main method, and the body is plus a variable x and variable y, close, close, close. That's our implementation map. I'm sure I've made some sort of syntax error there, but we'll come back to it later. And again, you'd actually read this in from the annotated AST. Scrolling back down, so now we want to look that up. We want to check in the implementation map and get out the formals and the body. So we're going to look up, we need to figure out, I'm going to match v0 with. And if it's a cool object with name X and attrs and locations, right? Fail with not handled yet, could be something else. Then we look up X and the function name in our imp map. And again, you may want to fix me, check to make sure it is there. If not, you have a PA5 bug. So now we've gotten out the formals, x1 through xn, and the body. We make new locations for each of the actual arguments. So, new arg locations. In reality, these would be on the stack. We pass arguments on the stack. Okay, there are new arg locations. We called new lock for each one. And now we make an updated store where in each of those new locations we store the corresponding argument value. So our store update, we just combine at each new arg location, we store the corresponding pre-evaluated arg values. So that's our store update. And we put that store update on top of, I guess this was SN plus 2. So SN plus 3 is the store update plus SN plus 2. This the @ sign is list append, and we're just doing it like that. And now you actually go to evaluate the body. But look again, we change this self object to be v0, the receiver object. Well, that's how you do function calls, right? We're sort of jumping to that object to execute this method associated with it. So we want to call ourselves recursively, and we're going to evaluate in v0 using SN plus 3. And now, this is a little tricky. There's a very special environment. And if you read this carefully, it has both the attributes of V and also the formal parameters. And the order matters because they could shadow each other. Right? So we want to put the formal parameters first and then have the attributes. So we need to build up this special environment. Right? Fix me, we should put the formal parameters first so that they are visible and they shadow the attributes. I am not going to do that. I'm just going to have the attributes be visible. Right? So this is not correct, but it's faster for now. And then we evaluate the body, which we got up here. And if all of that works, we just return the result. Let's see how far this is from compiling. Syntax error on line 216. Let in, let in, let in. Unbound value VO, you're right, it's V0. 206, new lock. Did I mean new lock? I totally did. 208, new arg locks. Did I mean that? Yeah, probably. 212, VO is V0. Yep. All right. 216, this case is unused. Good. And what was the other warning? We're never using old expression. All right. So now, when we don't need this old expression. When we do a new main, first we're going to assign x gets 5, then we're going to do y gets 7, and we expect the final result to be 12 somewhere, or we expect to see 12, kind of computed at the end of the day. All right. Big bucks and no whammies. All Right. So starting here at the top, we assign x to be 5. We assign y to be x plus 2, which ends up being 7. And it's not super clear. We don't ever actually seem to be evaluating x plus y. Let's go through. Oh! Yeah, we don't ever seem to be evaluating x plus y because I never actually called it. There's no dispatch expression. So what I'm thinking in my mind is that officially, where do they say it? Cool starts with class map. Maybe we say it at the bottom. You'd think I would be faster at the cool reference manual. All right, I don't know where it is in the cool reference manual, but I know something that happens to be correct. Implicitly, cool programs start with new main.main. That's a thing your interpreter does in order to actually execute the program. Right. So I want to do a dispatch expression on new main where I call main with no arguments. Right. And now we want the final result to be 12. This is what cool interpreters do to get started. You run new main.main. And here we see that the final result is 12 as expected. But this is good, or this is complicated, because it means that when we were evaluating this final x plus y expression, we were doing so in an environment where we could see x and y and where they had their post-initialization values. All right, that's actually pretty much it for this interpreter checkpoint. You will also want to do strings and internal expressions, like to handle outstring. But aside from that, you're pretty much there for outputting strings and integers. Of course, there are a number of things that I skipped, including line numbers for locations, actually deserializing these data structures. But hopefully the concepts made it across. And we'll just ever so briefly scroll through or review some of this. We had our cool abstract syntax tree expression types. Right? We had to define cool addresses and cool values. We're using association lists as our map data structure. An environment maps strings to addresses. A store maps addresses to values. You could use a hash table, but using an association list is a little more convenient in OCaml, but also forces you to pass around the store correctly, which is typically good practice. Here's our way of getting new locations. A class map, for us, maps class names to attributes and initializers. An implementation map maps classes and methods to their formals and bodies. Here's the program we were pretending to interpret. 5 plus 7 is 12. Here's the corresponding class map and implementation map. By the way, you may have noticed, in some sense, we never actually used the annotated AST. Yeah, that's fine. If you don't need it, it's redundant with the class map and the imp map. Here's our debugging and tracing, because getting this sort of code correct is very difficult, and you'll want to have more than just ad hoc printf debugging. And then this is the heart of PA5. This is the heart of PA5, a recursive procedure that implements the operational semantics. That's the plan. We pass in SO, SE, and an expression. We return a new value and a store. Lots of debugging, but the main heart of it is just a big match statement on every expression type. And for every expression type, you go through and you code up all of these. You just code them all up. It takes time, but it's fairly direct. many times you will end up checking to make sure that, when you're adding or subtracting, that the result is actually a cool integer. Or when you're doing if, the guard should actually be a cool Boolean. That's expected. But a lot of the heart of this is dealing with the environment in the store. And for assignment, variables, and new, we really saw quite a lot of that. We also saw how to use the class map and the implementation map. And then to run a program, you call new main.main. All right, that is it for today.